and welcome to this talk on reconstructing thermal history using two novel geochemical proxies. So as an introduction, I'm going to assume that everybody's already convinced that thermal histories are important because they give us some information, some indication on the diagenetic condition, the diagenetic history, but also, of course, the history of cracking of organic matter, oil emplacement. So really something essentially fundamental for oil and gas. So what I'm going to do here is I'm going to try to convince you that in carbonate settings, we have a new tool in our arsenal. It's one where we combine effectively for the timing of the carbonate uranium lead with laser ablation, and for the temperature component of that system, we combine effectively a clumped isotope with uranium lead. Right, and if you don't have the patience to watch the whole 20 minutes of the talk, I'm going to leave you already with a key message, which is to say that clumped isotope and the clumped isotope signature of the recrystallized limestone. Recrystallization is very, very important and very useful, although it is not the only thing that we can measure, is really offering us a new paradigm shift, a new powerful tool to reconstruct thermal histories in carbonate reservoirs. So very briefly, the methods. What is clumped isotopes? If you start with a carbonate, you can actually look at its composition, at its molecular composition. And of course, you will see that it's made up of a metal, calcium often, with a carbonate ion. Now, the carbonate ion is what we're interested in. So we're going to look more closely at the carbonate ion. And you can see that it is composed of oxygen and carbon of different isotopes, C13, C12, O18, O16. And that's what's interesting here. More specifically for clumped isotope, we are interested in the pairing of the rare heavy isotope O18C13 in a molecule. And we measured this relative to a stochastic distribution, and we call this CAP47. CAP47, this is a figure here from Peterson et al. In 2019. It's a compilation of all of the different calibration for clumped isotope that we have put together. And you can see that CAP47 varies with temperature. It's only temperature dependent, which is the interest of this proxy. And at low temperature, CAP47 is heavy. At high temperature, CAP47 becomes lighter. So we have less and less difference between stochastic and what we measure in our carbonates, which makes sense. Now, the other method we're going to use is ICP-MS, laser ablation ICP-MS. And as you can see on this figure here, what that allows us to do is to use a laser beam and get very, very precise, very, very small points that we can then measure for uranium lead composition. And for this, we use an ICP-MS. And when you do this, you get a range of different points. And these points have various degrees of mixing with common lead, and you can regress through those points to obtain an original or a clean uranium lead composition, which we can then translate into an age. So where did that story begin, that story of trying to do thermal history in our research group for using clumped isotopes for carbonate? Well, actually, it began a while ago in Oman, where we did a lot of field work. And we noticed that in this setting, we had some clay packages with nice, well-preserved, at least superficially well-preserved oysters. A quick look at the thin section, however, revealed that although some of the oysters were relatively well-preserved, quite a few of the oysters were recrystallized. Actually, most of the oysters were recrystallized, and some of them had also some evidence of silicification. So a much more complicated diagenetic history, and I thought it'd be interesting to do those measurements and see what we get. We also had dolomite in the region, and one of my other PhD students did some measurements on the dolomite. So I'm showing you here the results of both the oysters in red and the dolomite in green. And I'll start by pointing out on the vertical axis, you have temperature. On the horizontal axis, it's the back-calculated fluid composition. I'll talk about this later in the presentation. But what I want to point out is the well-preserved oyster comes up with a temperature of about 37 degrees, which is a bit on the high side, frankly. So there's probably a bit of diagenesis, but it's close from depositional. And actually, the composition of the fluid is about 1 per mil. So again, maybe diagenetic a little bit, but also potentially indicating some hypersaline conditions. So it's not an unrealistic temperature for this type of setting. However, most of the oysters and the dolomite point to temperatures of in order of 60 degrees Celsius. This is well above Earth surface condition. So we know this is not Earth surface condition for certain. So what's our observation here? Our observation is that the fine-grained dolomite and the recrystallized textures both yield similar temperature. And I think this is really exciting because it made me think that there was a potential application. So the application is potentially we could use fine-grained texture and recrystallized carbonates to derive a thermal history or thermal record for these carbonates. Because if we take this example in Oman and we look at the temperature we obtain, it suggests a burial of 1 to 1.2 kilometers, depending on your estimate of the geothermal gradient. So now fast forward to the PhD of Claire Veillard, who was focused on the dolomite of the Marion Plateau. We decided for her to work in this particular setup because we had some good ODP record. So we had access to a lot of material. We had shallow water dolomitization that was clearly evidenced by multiple evidence as being a purely marine early dolomite of Miocene age. And the maximum burial we had in this setting was only 600 meters. And above this, there is no overburden. It's just water, about 200 meters of water depth. So we knew that this was a simple setting. And we always like to start looking at simple setting first before we go into more complicated settings. So what do we see actually here? What's happening here? Well, we see that despite it being relatively simple as a setting, we do notice a lot of different dolomite textures from, almost well-preserved texture in the dolomite to complete loss of sedimentary texture and the deposition of effectively a very large dolomite of several hundreds of micron, even with dissolution of its cores. And long story short, when Claire did the measurement for clumped isotopes, what she noticed, which was a bit of a shock, is even if you look at the first 80 meters of the record, we see a change in the clumped isotope temperature of those dolomite. It starts in the order of temperatures in order of 15-18 degrees, so compatible with current day temperature of precipitation, if you want, on the seafloor. But already at a few hundred meters, you are looking at 40 degrees of clumped isotope composition. Now, this is actually suggestive of essentially a fully recrystallized setting. So that was really, really exciting because it does mean once again that these fine-grained dolomite are very susceptible to recrystallization, and potentially if we could pair this with an age, we could come up with some interesting thermal history. So now I would like to introduce you our third case study, which is the resolution GAIO ODP leg 143. And what I find really exciting about resolution GAIO is that it is completely isolated in the middle of the Pacific Ocean. It's a very simple Cretaceous carbonate buildup, right? It's composed of rudists and some sponges, a few corals, very classical carbonate for this time period, very similar to reservoirs in the Middle East. But the fact that it's isolated is exciting for the application of uranium lead, because it means that presumably we'll have less detrital lead, so a little bit of an easier time here dating our carbonates. And this is the reason why this particular setting was selected. The other thing is the sedimentary column at ODP leg 143 is pretty thick. We have lower Cretaceous carbonate of 1,600 meter in thickness. So that's quite a thick deposit. So we can actually really go and look at the detail of this thermal and sedimentology history. And Marija Guzarovic, my former PhD student, did exactly that. She sampled a number of things. And what she found in this gyro is that at the base, she had iron-rich brown dolomite that was sometimes mixed with a little bit of what we call the white dolomite, which is a coarser dolomite that is not iron-rich. This white dolomite is also found a bit higher up in the stratigraphy in a 50-meter window that is composed only of white dolomite, so iron-poor dolomite. And above this, this dolomitized section, we enter a section that is characterized by limestone, in which we find actually a number of interesting targets for clumped isotope, including vugs, recrystallized fossils, single crystals of calcite, and of course, micrite, or the limestone matrix. And Marija looked at all of these different textures. One thing to be aware of is that even though we have 1600 meters of sediment, all of these sediments are lower Cretaceous, and on top of this is seawater, because the gyro is now sitting at 1300 meters below wave base. It has been drowned at the end of the early Cretaceous. So there's again no overburden on this. So that's why, you know, the thermal history is of particular interest. So let's look at some results. And the first thing you can see in the results is we have a number of these different textures. The temperature at first appeared to be quite scattered. We have some cold temperatures in the order of 20 degrees and some warmer temperatures in the order of 50, 60 degrees. So there's a range of temperature. But on top of this, we can plot the current geothermal gradient. And because that gyro is at 1300 meters, the temperature at the surface of the gyro are at about 10 degrees, and the geothermal gradient that I plotted here in green shows that our cold textures match actually the coldest modern geothermal gradient. If we were to shift that geothermal gradient and push it to what it would have been in the Cretaceous, we obtain this red line. And again, what's interesting is that this red line forms the envelope of the warmest of our sedimentary texture. So between these two geothermal gradients, we find all of our clumped isotope temperature, which to me indicates that basically we've recorded throughout a history of recrystallization and cement precipitation a thermal history for this particular atoll. So now the game, of course, is to pair this with uranium-lead dating so that not only we know the temperature, but we also know when that temperature was recorded. And here you have it. On the horizontal axis, you have the age. 120 million years is on your right, and then 60 million years is on your left. So the time goes from right to left. And notice that I've indicated also in a dashed line the time when the atoll was drowned. Okay, so you can see that even though we record some texture that are pre-drowning, a lot of what we record happened actually post-drowning. Okay, so what can we tell about this temperature? Well, at first we seem to have a trend of temperature around 32, 33 degrees, very compatible with, let's say, Cretaceous surface water in the tropic. That seems to go to span from 120, maybe all the way to 90 million years. So we record things that are clearly superficial water, but that's of course not the only part of the story. We also see a trend to colder water post 90 million years, and in fact our white dolomite, this big white iron poor dolomite, shows pretty cold temperatures in the order of 20, 22, 23 degrees, so much colder than what we've expected in the Cretaceous. They're also dated as much younger by uranium-lead in the order of 75 million years. Also notice that we have some anomalies. A few of our data points plot at a relatively old age of 100, 110 million years, so pre-drowning or just after drowning, but with much warmer temperatures. So now let's look at the calculated fluid composition, because we can calculate the fluid composition from the clumped isotopes. And what you see here is that the fluid composition through time shows largely a pre-Cenozoic composition of seawater at around -1 per mil. So completely compatible with essentially marine settings. However, there are a few points here that diverge from this purely marine trend and seem to indicate much heavier fluids. So, at first thought, you'd think maybe those are brines and basinal brines, except that we don't really have a basin here. So what's happening? Well, to understand what's happening, I think we have to go back to that concept of water-rock ratio. What is high and what is low water-rock ratio. And in the case of a high water-rock ratio, an open system, delta O18 of calcite and or dolomite and Cap 47 temperature are at equilibrium, so we back calculate the actual composition of the fluid from which our sediments were deposited. When we are in a closed system or at very low water-rock ratio, the delta O18 does not change because the delta O18 is based on the bulk isotopic composition of the fluid, whereas the temperature recorded by clumped isotope, because clumped isotope is concerned with the arrangement of the atoms within the molecule, that actually is recording the actual temperature. So the fact that the delta O18 is still preserved as the pristine original depositional temperature, whereas the Cap 47 records recrystallization, leads to a calculation of a fluid composition that is wrong, and if the temperature has increased, it will give you a heavier delta O18 than what was really happening. So I think that what our records indicate is that we have some process that happen at high water-rock ratio, it's the green arrow there, and some process that happen in a closed system, or if you prefer, a low water-rock ratio. So let's try to look at the dating of the different events. So I've put here first, of course, the limestone deposition and platform drowning, which we've gathered from previous studies. What we see is that the first thing, the oldest record we have, the oldest phase we have, is this early dolomite that is iron-enriched. And that's followed then by several different processes, including the recrystallization of the brown dolomite, but also infilling of vugs and fine-grained cementation that seemed to straddle just the time when the atoll was growing and then was in the early stage of drowning. And then we have a second phase of diagenetic transformation that happen later and also often are recording colder temperature. And that's basically the coarse grain, calcite, and low water rock ratio fossil recrystallization. It's the recrystallization of the iron-rich dolomite into the white dolomite, the iron poor dolomite. I'm not going to go into the detail of why we think this is happening here, but we have evidence for this. And finally, we have some porphyric crystals, which are the youngest that we record at up to 40 million years, so Eocene age. We can now divide this into paragenesis. We can recognize one paragenesis that is phase 1, which is syn depositional or early drowning, and then phase 2, which is actually occurring mostly at high water rock ratio and is post-drowning and is influenced by colder water as the atoll is sinking. So based with this and with the depth at which these different events occur, we can come up with a thermal history for resolution Guyot, which you're seeing right there, because we can reconstruct paleo-geothermal gradients. We can superimpose on this our diagenetic phase 1. You can see that this is happening in the top warm tropical seas during deposition or during early drowning, where we're still into this very warm water environment. And phase 2, diagenetic phase 2, is happening later during drowning and starts to record much colder temperature, and it's just an effect of the drowning, effectively, that basically means that the carbonates are now in much deeper, warmer waters. So that leads me to my conclusions. I think that, and I hope I've convinced you, that pairing clumped isotope with uranium lead is a very powerful method. It gives you quantitative thermal and diagenetic histories. I think the benefit of the uranium-lead LAICPMS method is that you can do that at a very high resolution. Its drawback is that not every sample is datable. The benefit of the clumped isotope method is that it always works, but the drawback is you need relatively large samples. So pairing both methods gives you almost like the best of both worlds, because you will always get some form of information from your sample. And finally, I'll end up by saying that recrystallization is your friend. I think we can do a lot with recrystallized samples. We can do a lot of geothermal constraint in carbonate settings, which have been traditionally very difficult to reconstruct the thermal history from. Thank you for your attention.